We're starting chapter 5 in the textbook, which is transient conduction. And so if you want to start doing some reading, chapter 5 is the place. The first type of problem that we work in this chapter is zero dimension transient conduction. And the phrase that we used before and is commonly used is lumped capacitance. So zero dimension says that we can ignore the spatial variation of temperature and just look at the transient variation of temperature. The check to determine whether we can assume lumped capacitance is to look at the BO number, and its shorthand is just a BI, and it's defined as H, heat transfer coefficient, a characteristic length, divided by thermal conductivity for the material. And we'll have characteristic lengths that we use for a plane wall, a cylinder, or a sphere. And we're also thinking that the K here is for the solid material that we're, is going through this transient change. Just to think a little bit about where the BO number comes from and why it's used as the criteria. We want to think of these objects going through transient change, and these are my two spheres. And if I had sketched temperature versus radius, and maybe initially I'm at some high temperature, so I want that to look flat, temperature, and then it drops off pretty rapidly outside the sphere, so some free stream temperature. And so I know that with time it's going to cool down, so T increasing. And if my temperature with time looks something like this, oops, let's do it flat for longer and then drops down. This is a case when I assume lumped capacitance is valid. And I should say relatively uniform temperature. So if I sketched in this other object, okay. This other object, similar idea, temperature, and this is R. And initially I've got some pretty uniform temperature throughout, and it drops off outside the sphere. But all of a sudden I start cooling it off, and I see temperature variations throughout the sphere that are significant. In this case, lumped capacitance is not appropriate. So we'd like to think of something that has pretty high thermal conductivity so that heat is able to transfer through the object relatively easily. So our BO number is resistance to conduction. And if I think about just a plane wall, so I'm going to write L over KA, and resistance to convection 1 over HA, and we can cancel the A's. Surface area is same for these this object, and I'm left with HL over K. And so there we have our BO number. And again, it's saying the fact that we want it small, we want a small resistance to conduction, and then resistance to convection is more significant. It's a larger value. The characteristic length the general definition, if we get away from something You will see plane walls and cylinders over and over, so you get used to what the characteristic length is. But if you have some other object, the general definition is that it's the volume over surface area. And if I think about a plane wall, and that's my center line, and a lot of times we make the thickness of the wall 2L, so that half of the thickness is 1L. And if I write my definition for characteristic length, the volume would be 2L, and I'll just use a surface area. And the surface area, because I have two faces now that could be exposed to this changing temperature or changing surface condition. And if I cancel those, I get that the characteristic length for a plane wall is just the L, the half thickness of the wall. For a sphere, and you'll see that it's R over 3, and for a cylinder, you'll see that it's R over 2 for a characteristic length. A general lump capacitance problem I most often think of as we have some object that is suddenly exposed to a different boundary condition. And normally I think of that as a convective boundary condition. And that happens pretty commonly when you're quenching an object, or you take something out of the furnace and you blow cool air over it to cool it. But there can be more than the convection, and our book sets up the general lump capacitance problem, so not just convection. And so this is our basic energy balance equation, and we can have heat flux to the object, convection off to or from the object, radiation exchange, generation, and then here's the transient term over here. This is a difficult problem to solve, and so the next topic in your book is to look at components of this. If we can make some simplifications, we can come up with some easier solutions. And there are ways to solve this whole equation with all of these complexities, but for our purposes, we're going to look at some of the simplifications. If you notice, these areas are different. So, for example, this first one has surface area, and it's got a little h. And then there's a C over here, and there's an R. The idea here is that you don't have to have the same surface area for heat flux, for example, to be applied to the surface. In this plane wall, they're showing maybe I have heat flux on one of the surfaces over here, but it doesn't have to be over the total area of the object. And likewise, convection, I can have that acting on a particular surface. So they distinguish between these areas. Some of the cases, convection only, and in my next couple slides, we'll look at the case where we're just considering convection. Radiation only. There is a nice solution to that, and it's given in the textbook, but I'd say that's a pretty unusual case. If you have drawn a vacuum so that you have no medium surrounding, and so that you can't have any convection occurring, that you only have radiation exchange. The third one down is negligible radiation, but it does allow you to consider heat flux applied, convection occurring at the surface, and volumetric generation. And it has a solution given for that also. And each of the terms you can see when you look at the formulation. If you don't have volumetric generation, you just set that term to 0. It can use that same equation. So I'm just saying that it may be useful. You may find a particular problem where you do have multiple effects to consider. And then the last one, convection only with variable convection coefficient. Um, so in our case 1 up here, we have convection, but it's going to be a constant value of convection. But when you have free convection, convection that is driven by a temperature difference, this is the case that may be useful, is this convection case, but it has variable convection coefficient. So if we look at the convection-only case, and I have put a slide up that has some of the equations, and we want to talk about this top case first. And I'm just going to a blank slide for a minute. Okay, so this is where we have convection off of the surface, and we have an environmental temperature, free stream temperature that's constant. And if I was looking at the energy balance, so the surface energy term due to convection, and then the storage term, we can make the substitution that T minus T infinity is theta, and then we separate variables. And we can integrate both sides, and I would put my limits in that normally we're going to start at t equals 0 to sometime t, and theta initial to a final theta. And just to remind you, so theta I is going to be t initial minus t infinity, and theta final is the temperature that we end up at minus t infinity. And depending on how we want to work these equations, often we're interested in the length of time to get to a certain temperature, or sometimes we're asked what is the temperature of the object after a given time. Okay, so I still didn't integrate this. And if I'd like to get rid of the negative sign, I can flip the order, this fraction inside the natural log. Okay. All right, now we can go back to this previous slide. So this is a useful result for lump capacitance problems where it is convection is dominant, the mode that we're considering. Let's go back to this slide. So this equation is a slightly rearranged form of the equation that we just talked about. The one thing that they have done is they have put together a definition. They call it a time constant, tau, lumped for this lumped capacitance object, and the value rho volume of the object divided by C sub p, divided by HA surface. So that combination of parameters we saw before that made the equation look bigger, now we've redefined it as this time constant and inserted it into the equation. The time constant does have a physical meaning. So if you think about the if an object is initially at T initial and we got a free stream temperature that it's now exposed to, ultimately it's going to go to the free stream temperature. So the biggest temperature difference is T initial minus T free stream. And in one time constant, that object will go to 63.2% of that temperature difference. So we're going to, if we put it in a cool stream temperature, T infinity, it's going to go 63.2% of the way to getting to that free stream temperature in one time constant. Okay. The next equation listed here, and I need to cite that this came from the textbook, heat transfer by Nelson-Klein, is if I had an oscillating free stream temperature. And it also notes here that this equation is valid once the initial transient has died out. So we have a periodic pseudo steady state situation that it's now oscillating, but in a steady state way. So if we looked at this next slide for just a minute, so we're imagining again we have some object, and this is pretty common if you're doing temperature measurements. So you might think of the thermocouple as this small object, and it is in a free stream temperature that is oscillating. So if I look at this figure, it's got a fluid temperature given, and it's got a significant oscillation, 100 degree, maybe not quite 100 degrees C temperature variation of the fluid. And then there is an object, the sensor that's inserted into the flow, and it's showing the response of the temperature sensor. And it is significantly different, and it has to do with the thermal capacity of the sensor, that it can't follow this quick temperature cycling of the free stream temperature. And a way to determine how far it is, how different it is, and again, we can see that there's going to be an amplitude difference, but you can also see that there is a phase shift. So the sensor lags the actual temperature variation. Okay, so if I go back to this previous equation, and we've got our same lumped capacitance time constant, we've got omega, the frequency of oscillation of the free stream temperature. I think everything in this equation is defined, but it gives you a way to determine how well this temperature sensor can actually match what the free stream temperature actually is. So how that differs, and also the phase lag between those two temperatures. The last case that is listed here is for a ramped temperature. So if you had an oven that was heating up, so temperature versus time should be a constant slope line, and they give the beta is our rate of temperature change with time. But due to the fact that we have capacitance of the temperature sensor, it does not quite follow the temperature change of the line, and this equation can be used to calculate at a given time instant what the response of a temperature sensor would be to that changing free stream temperature. So this concludes the introduction, and the next lecture will be to work through a problem or two.